This recording is for Primary Math 5 from the Challenging Word Problems book, pages 7 through 10. Page 7, number 1, starts out with a number that is divided by y and has a quotient of 16, with a remainder of 3. Then it tells us the sum of the numbers and the quotient and the remainder is 345. I want to show you two ways to work this one. When it says that the number x is divided by number y with a quotient of 16 and a remainder of 3, this is a visual of what we're talking about. Orange is the number x. If I divide it up into groups the size of y, I get 16 of those, and there are 16 green boxes here. There are 16 y's all the way through, plus there's 3 extra in addition to that, and of course the assumption here is, and the understanding is, that these are the same size, that x is the same thing as 16 y's and 3 more. Then it tells us the sum of the two numbers. So if I add x and y, the quotient, that's the word for the answer to a division problem, that's 16, and the remainder, the sum is 345. So that's our starting place with this. Now, the next thing we can do is look at this, and I'm going to do this another way in a minute. This is, anyway, two ways. This is the shorter way, but it's a little more abstract. In a minute, I'll do it another way that is similar to what we've done, more similar to what we've done in class. What I want you to see, and what I want you to help your students to see is this. I have x. I have another name for x. Another name for x. X is the same thing as 16 y's plus 3 more. I like to tell students that this is like a nickname. Just like some people call me Mrs. Barnett, some people call me Mom, some people call me Brenda. Nobody gets confused. My children are not confused when I'm in a room and somebody else calls me Brenda and they call me Mom. It doesn't confuse them because they clearly understand that I have two names. More than that. So when you see things like this, understand what we're saying is that this is a nickname for the other one. So if I take this value of x and I write, instead of x, I put its nickname in that spot. That's a skill we do in math a lot. Now, again, as a parent, you might recognize this is a full-on Algebra 1 problem. Don't tell your student that. And if your student watching, forget I said that. Because really, this is what Singapore Math has led us up to being able to do. We can take this and we can see that we're going to put our y's together. So all together now, I have 17 y's and 22 is equal to 345. Well, again, without worrying about the algebra, you know that if you have to add 22 to get 345, before I added 22, I must have been at 323. And if I was at 323, then if 17y, let me just start it back up here, a little bigger. If 17y is equal to 323, I paused and did the division. I even did long division this time. It's not a bad thing to do long division. Sometimes it's just mental math is more work. So the value of y is 19. The question asks us to find the value of x. We know that x is 16 y's plus 3. I'll pause. I did long multiplication. I should have said 20 16s, subtract 1 16, but at any rate, 16 times 19 is 304 when I add 3 back in, because remember x is 16y plus 3, then I get the value of x is equal to 307. Now, that is certainly a challenging problem, but if you set it up this way with your students and understand what it means to say that x divided by y is 16 plus 3, and then if you can get them to the point of understanding the idea of a nickname of a variable, then the rest of it is very much stuff that we've done in the past. Now, what if you want to do it an alternative way? We will look at number 1, part 2, the alternative way. You can do this one with a guess and check. So I'm going to set up a chart and turn it back on when I get that set up. I would use a chart something like this to solve it. Notice at my top of my chart I have the y variable. I'm just going to pick a number. I'm trying to find that and decide which y value makes it work. And then I'm going to find 16y plus 3, which is another name for x. And then I'm going to find the sum of the two values and the quotient and the remainder, which is the same thing as the sum of the two numbers over here plus 19. So I might start with, I just have to start somewhere and decide if I'm too big or too small or what I'm doing. If I let y be 10, 160 plus 3 is 163. If I add that, 163 plus 10 is 173. Plus 19, remember to add 20 and go back 1, that's 192. I know, by the way, that I'm trying to find one. I'll know that I've done a good job when I get this column to be 345, because I want this sum and the numbers and whatever to be 345. So far I'm not there. I'm at 192. Maybe I should go up a good deal and see what happens. If I go from 10 to 20, 16 times 20 is 320 plus 3 is 323. And then I have 343 plus 19 is 362. Now I know I've gone too far. I want to be at 345. I am currently at 362, and so I'll just cut us a break because I know from the last page the answer is 19, but clearly it is not far from 20. So whether you try 19 next, whether you try 18 next, whatever you would do to solve this, I shouldn't write it down like that. Okay, again, this time we'll work on mental math a little more. 20 times 16 is 320. If I only have 19 16s, I'm going to subtract 16 from here and get 304. And that gives me 307. If I combine 307 and 19, that gives me 326. And I add 19 again, and certainly I, hooray, hooray, come up with 345. And so that tells me that my two numbers, again, it asks for the number, the x value and the y value. So my y value is 19, my x value is 307, and I'm sorry, actually all the question asks is, what is the x value? And that answer is that it's 307. Now this way is largely in keeping with what we've done in the past. It's a good, solid, organized guess and check. The one on the first page is how they show it in the back of the book, and it's very appropriate to demonstrate to your child how to do the problem both ways. Let them work on it. Number 2, at the start of the trip, Frank's car has an odometer reading of 12,321. It calls it a palindromic number, and the little Gumbo-looking guy over there, Gumby, is that his name, says a palindromic number reads the same forwards and backwards. So left to right is 1, 2, 3, 2, 1. Right to left is 1, 2, 3, 2, 1. According to our problem, after driving for 2 hours, the odometer showed another reading, also palindromic, and if Frank was driving below a speed limit of 100 kilometers per hour, what was his speed? And so, a couple ways you could do this. In 2 hours, at 100 kilometers per hour, he went at most 200 kilometers. And it actually says he was driving below 100. So at 2 hours at 100, he'd go at most 200. So we know he went less than 200 because, again, the words are very particular. It's not possible that he's driving 100 kilometers an hour. He was driving at a speed below a speed limit of 100 kilometers per hour. Okay, so we know that he went less than 200 miles. Your child might look at this and immediately say, well, the next time you're going to have a palindromic number, remember, the 1 and the 2 can't change very fast. You can't go 1,000 miles anytime soon. And so if that 1 and 2 are the same, then you have to have a 1 and 2 out there, and this middle number is the only one that can change. So if you've gone less than 200 miles, you must have gone 100 miles, and your new palindromic number is 12,421. So if the new palindromic number is 12,421, and he drove for 2 hours, what he actually did was drive for 2 hours, and he went 100 kilometers. So in a speed, because it asks us what was his speed, a speed is given in kilometers per hour. He went 100 kilometers in 2 hours, so that's a speed of 50 kilometers per hour. Actually, the book writes it with a line. Doesn't really matter. When we do miles per hour, we usually put a P for per. When we do kilometers per hour, they put the slash line instead. Same thing. Number 3, the product of the ages of 2 adults is 770. So if I took the age, we'll just use X and Y because there's such nice math numbers. If you multiply the age of one times the age of the other, that's the product, right? Remember the product is multiply. You get 770. The question is, what is the sum of their ages? Well, first we have to find out what their ages are. And we need to find the factors of 770. A couple of ways you could do that. I'd like to teach you this way in case you don't know it already. I can look at this and factor and say, well, that's 77 times 10. And 77 I know to be 7 times 11. And 10 I know to be 2 times 5. And these are prime numbers. Every factor of 770 can be found in one of these numbers. I could say it's 2 times... there's a 2. I can multiply the rest of those and come up with 385. 7 times 11 times 5 would be 385. I could say it's 5 times. If I use the 5, then I say it's 77 times 2 is 154. 7 would be times 110. I could find all of the numbers. If I use the 2, then I have to multiply 7 times 11 times 5 to get 385. If I use the 5, I have to do 2 times 7 times 11. If I multiply the 7, it's 2 times 5 times 11. I think this understanding factors and how you come up with all of this is an important part of math that we often skip over. Once I've used all of my numbers individually, I think this last one through 10 times 7 is 70, of course, because this is 2 times 5 times 7. Then I can start pairing them up. And I could say 2 times 5 is 10 times 7 times 11 is 77. Okay. Now, all of this are things that I can do to find all the different factors, but let's get back to our problem. The problem wants to know the ages of 2 adults that has a product of 770. All of these numbers that I've written down are factors. If I multiply 2 times 385, I get the right number. But the problem is, so far I haven't had any that are arguably an age of adults. When I get down here, I get 10 and 77 and 14 and 55, but 10 and 14 don't really qualify as adults. So all I'm really doing, and again, this is all for teaching and understanding what we're doing, but all I have to do really is look at these and find some pairing that is going to give me two numbers that are adult kind of numbers. And so when I look at this, without doing all the stuff on the right side, because I already understand factoring, I can realize that my adults could be 22 and 35 years old. And that takes care of all the factors of 770. It's a reasonable age for two adults. And remember to look back at the question. It's not how old are they, it's what is the sum of their ages. 22 plus 35 is equal to 57, and that is the sum of their ages. Number 4 is going to require another chart. Alright, so we're beginning with the top information. We want a 3-digit number, and here's 2 qualifications for this 3-digit number. It has a remainder of 7 when I divide it by 9. So when I take this 3-digit number, divide by 9, I have a quotient, and then I have a remainder of 7. But if I take the same 3-digit number and divide it by 5, I'll have whatever quotient, but a remainder of 2. So I wanted to kind of draw that out and get an idea of what's going on. The hint says, show that the smallest 3-digit number is 142. That kind of spoils the fun. You might want to mark that out for your student, but whatever. If I take a number and divide by 5 and have a remainder of 2, we understand 5s pretty well, right? We have 5, 10, 15, 20. All of the 5s end in a 5 or a 0. And if I have a remainder of 2, then that means I must have started with a 7 or a 12 or a 17. Any number that meets this criteria, okay, if I divide by 5 and have a remainder of 2, that number is definitely going to end in a 7 or a 2. Again, remainder theory is important. Hopefully by now that's starting to sink in. And so I made a list of 3-digit numbers, and every one of them is going to end with a 7 or a 2. Once I have that figured out, I don't have to write all of them down. I just need to kind of figure out what I have. Then I have the next part of it to figure out, and that is if I divide by 9, I have a quotient of 7. Well, I started with one that I knew. 99 is divisible by 9, and if I add 7 to it, I'm at 106. That number is a 3-digit number. If I divide it by 9, it's going to go 11 times and have a remainder of 7. And then from there, if I have 108 is the next one, and add 7, I get 115. Notice the difference between these is always going to be 9. Because if I'm counting by 9s and I'm always adding 7 to it, this distance is 9 as well. Remember, counting by 9s is really pretty easy. The digits are going to go down. 6, 5, 4, 3, 2, 1, 0. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And the tens digits goes up, right? So 106, 115, 124, 132, 140, sorry, I said wrong, 133, 142. I know, even though I don't carry this list down, that somewhere down this list, 142 is going to be on this side too. But I also know that if I go a little further, I'm going to come up with one that is a 7 on the outside. When I continue my list, I come up with the next one that's going to have a 7 in that spot. And what I find out is 187 and 142 subtract to have a difference of 45. Now, if you continue that list of 187, you'll find that the next time that you come up with a 2 on the end is the number 232. And there's also a difference of 45 between those numbers. So what I'm finding out is every 45 numbers starting at 142, I will have one. I will have a 3-digit number that meets both of my criteria. So I'm still on the hunt to find how many three-digit numbers make that work. So on the right side of the page now, I said, okay, from 1,000, if I go back to 142, which we've already found to be our first number that meets both criteria, if I go back there, there's a space of 848 numbers. And if I say, well, I'm going to count by 45s, how many 45s can I count? How many times can I jump 45? You know, if I start on the number line, I start at 142 and I count by 45s, how many 45s will there be before I get to 1,000? Now, notice I don't expect to land on 1,000, right? At some point, I'm going to go there and it's not going to hit 1,000, so it doesn't have to be exact. So if I do 858 divided by 45, I'm going to use some estimating because I know that 900 divided by 45 is 20. And so if I go down 45, then I know 855 divided by 45 is 19. And that tells me there's going to be 19 jumps. Before you land, and the next jump you'd be a 4-digit number. Now, one more little trick on this. Do you remember when we started out the year and we did some problems and we did it the other way? And we found out that if you have, I'm not sure which level this was in, but this is the kind of problem. If you have 5 trees planted and the distance between each tree is 20, right? 5 trees only has 4 spaces between them. So in our case, we're going backwards from that. We have 19 spaces, so that means there are 20 numbers where that happens. So we've got to get used to that oddness in both directions. Okay, in Singapore math, you've had problems that you say there's a tunnel and there's a certain number of light posts in the tunnel. We're trying to find out how long is a tunnel, and you realize that the number of light posts and the number of jumps between light posts is 1 apart. So this is the same problem from the other direction. From here, I know that there are 19 jumps from 142. I can count up 45 19 times. So those 19 times each land on a number, but this 142 also has to be counted. That would be your 20th number. Number 5. At an election, 240 votes were cast by 4 candidates. The winner won by a margin of 8, 13, and 15 votes over the other candidates. So we'll call person A the winner, and we'll say that person B was the next up, and he lost by 8 votes, and person C lost by 13 votes, and person D lost by 15 votes. So what we're actually saying, of course, is that if I made these equal, I would have to add 8, 13, and 15 votes onto each of those candidates. And we know that there were 240 votes cast. We're trying to find the lowest number of votes received by an opponent. Clearly, if I combined these 3 numbers and added them to the votes cast, 8 and 13 and 15, 10, 20, 36, is 276. If there were 276 cast, all 4 candidates would have an equal amount of votes. So when I divide that, I get 69 votes for each of those boxes. And again, this is if we all had the same size. So this box is 69, The question it wants to know is what is the lowest number of votes received by a candidate. So this guy got 69 votes if he got all of them, but he had 15 less than that, so he had 54 votes. Number 6, 2 watches and 1 calculator cost $49 in all. Rather than trying to draw a watch and a calculator, I'll just use letters. If I go to the store and buy 2 watches and 1 calculator, I have to spend $49. If I buy 3 watches and 3 calculators, then they tell me it's $99. And the question is, what is the cost of 1 watch? That's what we're trying to find. Now the hint is, what is the cost of 1 watch and 1 calculator? That might give you an idea of how to go. These kind of problems, treat them like puzzles. I think they're very fun. They're, of course, again, we're of course setting up for later math classes. And so understanding this problem will help you very much in an Algebra 2 class someday. But the idea is this. Notice that I could take this purchase and I could group it into 3 equal groups. That'd be the same thing as if I walked into a store and bought a watch and a calculator, a watch and a calculator, and a watch and a calculator 3 separate times. So if I took this $99 and divided it by 3 and got 33, what I find out is I spent $33 on this set, $33 on this set, and $33 on this set. Keep in mind I can't divide it by 2 and know the cost of a watch and a calculator because I don't know that they're equal. But I do know that if I have 3 equal sets of a watch and a calculator each, that each of them is $33. So what does that tell us? Hopefully it's jumping out at you by now. A watch and a calculator together are $33. So I spent $33 on the watch and calculator, but I had to give them $49 because I got another watch. So that other watch must be $16. And that's what they ask us, is what is the cost of 1 watch? So the watch is equal to $16. Number 7 is a similar problem to number 6. They're all similar, but the way you solve them isn't the same, and that's good because it teaches us lots of thinking skills. We have 2 bags and 4 hats, and that costs $100. 3 bags and 7 hats. Here, I drew it so you didn't have to watch it all happening. What can we do with this? It's not quite as simple as the last one. It doesn't quite break out that way, but I can look at it, and we can, you can change the proportions of the numbers. If I can buy 2 bags and 4 hats for $100, then I can buy 1 bag and 2 hats for $50. That's the logical leap you have to make. If you make that leap, then I can go to the next problem and say, well, there's a bag and 2 hats, and here's a bag and 2 hats, and here's a bag and 2 hats. And each of those groups cost $50. So I spent $150 because I got 3 groups of a bag and 2 hats, and I have another hat, and I paid $164. Guess how much money I paid for the hat? The hat was $14, and that's a question they're asking. Now, you may be thinking, What if it doesn't work out evenly? Well, that's kind of the key. In these problems, they have to give you something to make it easy to work. That's why it's not an Algebra 2 problem, because you can solve it logically and not have to go into deep algebra and lots of maneuvering to do it. You just have to find the one logical leap that makes it a possible solution. Number 8. I'll draw it. All right. In this problem, I have 3 watches and 5 lamps, and then I have 5 watches and 3 lamps. Nothing is divisible. 3 and 5 don't simplify out. I can't cancel one out of the other. One has more lamps, the other has more watches. Not much I can do, but again, the hint is convenient. But in this case, what I could do is say, well, maybe I went and did this on 2 different days. What if I bought all of these on the same day? Then I would have 8 watches and 8 lamps, and I would have had to spend $384. Again, I cannot divide that by 2 and tell you what a watch or a lamp is, because they're going to be different prices. But I can say that 384 divided by 8 will give me the cost of a lamp plus a watch. I have 8 pairs, and those 8 pairs add up to $384. And I drew that down here just to help you make it really concrete. I have 8 pairs of watches and lamps. If the total cost is $384, I can divide it by 8 to get the cost of the lamp and watch together. I cannot use this yet to find the cost of one lamp or one watch. But if I do 384 divided by 8, then I get that a lamp and a watch together cost $48. Now, how does that help me? Well, I go back to my problem and I say, that's $48. That's another $48. And that's another $48. So I have 48 times 3 is 144, and I buy 2 more lamps, and I spend $176. Those 2 lamps must cost me $32, and that means that 1 lamp is equal to $16. A whole lot more logic than math in these problems. And it may be a struggle to really work through them, but look them through, practice them, try them. I think they'll begin to make sense. Every time we have a pair of lamps and watches, it's $48. So these 3 pairs represent $144 of my spending. And the other $32 that I spent had to have been used to pay for 2 lamps. And if 2 lamps are $32, each of the lamps is $16. Hopefully that's clear. Problem number 9. In this problem, we're told that 3 calculators cost as much as 7 mugs. Okay, again, I took the time to draw it without having the recording turned on. We're told that 3 calculators cost the same as 7 mugs. That's the first thing to realize. Second thing it tells us is that a calculator costs $12 more than a mug. So here's my mug. This bar represents the cost of a mug. A calculator is the same as the mug plus 12 more. Now, then I made this graph. 3 calculators, again, remember this is a nickname. I could call the calculator C, or I could call the calculator bar plus 12. This is 3 calculators is equal to 7 mugs, using the bars instead of the letters. At this point, look what we can see. If I got rid of, now remember these are equal, okay, think of them as being on a weight right, on a lever where they're all sitting equal, okay? And if I have a bar and 12, and a bar and 12, and a bar and 12, what I'm doing is taking away a bar. These are equal, that's what it means. If I erase a bar from each side, then the weights are still equal. And I erase 2 bars from each side, and the weights are still equal. Now I've erased them on the left side, and I actually just marked through them over here, but what we see on this side is that I have 36 on one side and 4 bars. Same thing here. Again, we want to show them in a concrete way what we're doing. And then once they understand it, you don't have to forever draw all the bars. You begin to understand it and not have to draw so much. But what we're now able to say is that 36 is the same thing as 4 bars. So each bar must be equal to 9. And the question they're asking is, what is the cost of a mug? The mug is $9. Isn't that amazing what we can do with a picture? Last problem is very similar. 3 jackets cost the same as 5 shirts. Each shirt is 16 less than each jacket. So a jacket and a shirt, we could do subtraction. Generally speaking, I like to keep it to addition because addition is just somehow easier. So instead of saying a shirt is 16 less, I'll write it down as a jacket is 16 more. That's my preference. You can do it either way, of course. And what I know is 3 jackets that's 3 jackets are the same as 5 shirts. So if we take our equal weights and we get rid of 3 boxes on both sides, we now have that 48 is the same thing as 2 boxes, or one of those is equal to 24. The question is, what is the cost of one shirt? And we just found that a shirt is $24. And that is all of the word problems for this section.